thank you all for joining, and thanks to the IPAM staff for setting this up. I know this is still quite early on the West Coast. Today I'm going to talk about, related to the theme of the conference, some of the recent results on applying PDE tools to understand the sampling dynamics, and also a very recent work on understanding generative models. This has been joint works with two students, Yu Cao at Duke, who is actually going to be a core instructor starting next semester, and Lihan Wang, who is a fourth-year grad student, and also a postdoc, Yulong Lu, who is going to UMass starting from fall as an assistant professor. These guys are really the who did the work, and they are rising stars. Keep an eye on them. Okay, so the topic of my talk is on sampling. Okay, so I guess I don't need to introduce to say that sampling is a very important problem and arising from many different applications. In particular for this conference, perhaps people are more interested in machine learning and Bayesian statistics, but I'm more coming from a computational physics background, so it's also rise up in many applications in physics, including statistical mechanics and many-body quantum problems. And of course, since the problem is so important over the years, many methods have been developed, such as Markov chain MCMC. I guess probably everyone is familiar with that, like diffusion-based sampling, which I'm going to talk more about later. There are also methods that not just using a single Markov chain, but using a few of the interacting species or interacting samplers, like particle filters or replicate exchange methods. And also more recently, due to the success of deep learning, and there have been also considerations of applying some of the tools developed over there back into scientific computing, including sampling. And in particular, there are a lot of interest in generative models these days, like normalizing flows and the GAN, generative adversarial networks. All these things, there are a lot of activities these days. So in this talk, I'm going to mainly talk about two recent results from our group. The first one is we're trying to use the PDE tools to understand what's the speed of convergence to equilibrium of Langevin dynamics. Let me clarify that by Langevin, in this talk, I always mean underdamped Langevin or physics Langevin, not like the statistical Langevin dynamics. This is joint work with Yu Cao and Lihan Wang. And then in the second part, I'm going to talk about how the PDE analysis sheds some light on understanding generative models for high-dimensional probability distributions. Okay, I think as Dimi said, if you have any questions, you can just let Adam know, and then Adam will interrupt me, and so you can ask. All right. So the first part, the Langevin dynamics. So this is Langevin dynamics in the physical variables, and x is the position, and v is the velocity. So this is just a definition of velocity, essentially. Velocity is the derivative of the position. The second equation is really the key part of Langevin dynamics. So this is essentially the Newtonian second law. So this is mass times acceleration equal to a force, external force, that's given by potential that of the system. So where I denote U by the potential, and this is a gradient field. But then the Langevin dynamics models a particle interact with the environment. So the environment has two effects. One is the dissipation, which is this damping term. So you think about, for example, a particle moving under some thick liquid, and so that the inertia will be damped by this damping parameter gamma, which is the friction coefficient. And then you also think about that maybe the environment has some very small particles that hit the huge particle down under consideration randomly, so that there will be also noise coming from the environment. And the noise is modeled by Brownian motion. Okay, and then these coefficients here, you may ask why there is a gamma also appears here. This is known as the fluctuation dissipation relation dated back to Albert Einstein, and we'll come back to this later. Okay, and this is, of course, Paul Langevin, who write down this equation to model particles interacting with the environment. Okay. So for simplicity of notations, and also to highlight the main part, from now on, I will set all the physical parameters except gamma to be 1, okay, after some possible non-dimensionalization and rescaling of the equations. So in the end of the day, this is the Langevin dynamics we are going to consider, with only the friction parameter being a brilliant parameter here. All right? So, if this is the first time to see this equation, one way to understand this is that if you set gamma to be 0, right, then this is nothing but Hamiltonian dynamics, because I mean, the first equation is really just the position is equal to the derivative position equal to velocity. The second equation is velocity is the acceleration is equal to the force. Okay, so in particular, this the Hamiltonian dynamics is associated with this Hamiltonian, which is the usual kinetic energy plus a potential energy. All right. Now the other limit, which actually you send gamma to infinity, is also interesting. And when gamma goes to infinity, of course, then these coefficients are really large, right? So that on the order 1 time scale, x is essentially, freezed by v, and v reaches to equilibrium according to this equation. And if you do some math, I'm here deriving this very heuristically, just setting that, okay, so v is equilibrium, so that I set the right-hand side to be 0 and plug in the first equation. But you can make all these things rigorous. And then after rescaling, you see that because v is proportional to 1 over gamma, so that x is moving slowly. So you have to rescale, so that you have to look at long-term dynamics. And after rescaling, you get this equation. Okay, and this is actually known as the overdamped Langevin dynamics, because you are thinking of a regime that friction is really large, so that the particle loses its inertia, and so that the position is only changed due to force and plus some random kicks. All right. So this is overdamped Langevin dynamics, and now, because Langevin dynamics is SDE, right? So that one thing that we learned, like in the first class of stochastic calculus, is that to understand the behavior of, the evolution of this equation, it's very helpful to write down the associated, the mass equation, or in this case, I write down the backward Kolmogorov equation. And for the underdamped Langevin dynamics, this is known as the kinetic Fokker-Planck equation in the PDE literature. And the equation is given by this. So this describes the evolution of the observable under this Langevin dynamics. So f is a function that depends on time, position, and velocity. And let's say that initially it has some value, which is given by f0, and the evolution is given by the generator, the infinitesimal generator of Langevin dynamics. And because the Langevin dynamics consists of 2 parts, one is Hamiltonian, the other is this dissipation and fluctuation. So the generator also corresponds to 2 parts. And now you see that why I actually scale these parameters in this way, because now the fluctuation dissipation part has this form that is this operator, which is like an OU process in the velocity variable times the parameter gamma. Okay, and so that if you scale in this way, then naturally the gamma stands out here. And then you also have the Hamiltonian part, which is the usual Hamiltonian generator for the Hamiltonian dynamics. Okay. And one nice thing is that after you have written down the generator, you can explicitly check that the invariant measure, actually under some very mild conditions, this is going to be unique invariant measure, that of the Langevin dynamics is given by the following expression, which is essentially the Boltzmann distribution of associated with Hamiltonian, and z is a normalization constant. And also remember that I set all the physical parameters except friction to be 1, so that there was no beta here. Okay. And or if you write down more explicitly what the invariant measure is, the invariant measure in the x variable is essentially just given by e to the minus u, and in the velocity is essentially Gaussian. All right. And because of this, right, so that the dynamics, the invariant measure is this thing, so that now if we turn it around, right, let's suppose that we want to sample a measure in x, which is e to the minus u. Of course, given any measure, you can take a log of it and write it down in this form. Right, and then you can simply run the Langevin dynamics to sample that. And so this is what I said, what I wrote here. This is the invariant measure. So suppose we want to sample this, we can just run Langevin dynamics. And of course, this idea is not really new, and this has been discovered, I guess, more than 40 years ago. First by chemists, and they call it smart Monte Carlo. So it's by this paper. Actually, they propose, the 2 possibilities, either using the Langevin dynamics and also the overdamped Langevin dynamics to drive the MCMC. Okay, and because this is a really nice idea, it has been rediscovered for many times. And in particular, in the stat literature, the overdamped version is rediscovered, and this is named as MALA, so metropolis adjusted Langevin algorithm. And because when they rediscovered this, they dropped the overdamped, so that usually in the stat world, when people say Langevin, it means the overdamped version. But as I said before, in my talk, Langevin means underdamped. Okay. So and also the MALA, the convergence of MALA has been already analyzed by Robert and Treaty back in 1996. And also instead, usually people use the overdamped version, but also in recent years, the underdamped version starts to catch attention. For example, you can read this paper by Michael Jordan and collaborators back in 2018 in the machine learning literature, where they try to analyze the convergence properties of underdamped dynamics. And this also has been tightly connected to the so-called hybrid Monte Carlo or the Hamiltonian Monte Carlo method, because the Hamiltonian part of underdamped Langevin dynamics is indeed Hamiltonian Monte Carlo, very similar, and then the noise part that acting on velocity is very similar to the HMC, where you resample the velocity variable from time to time. Okay, and as I also mentioned that here, that I actually mentioned that many of these methods actually combine the Langevin dynamics with the metropolis acceptance rejection. But people already in 1993, Neil has already realized that actually you can do it without acceptance rejection, and if your integrator is accurate enough, it's actually also okay. All right. Okay, so now, as I said, the main question that I'm interested in here is that how fast this Langevin dynamics converges to equilibrium. And I'm going to ask the question from a PDE perspective. So in the PDE language, this is saying that if we look at this kinetic Fokker-Planck equation, and obviously it's very easy to check because the generator, because the rho infinity is the invariant measure, so that the integral of my function f under the time evolution with respect to the invariant measure, this is a constant in time. This is conserved. Okay, so in other words, if you start with f0, and if my invariant measure is unique ergodic, then you would expect that as time goes to infinity, from this backward equation point of view, that my f will converge to a constant, which is just determined by the integral to the invariant measure, with respect to the invariant measure. But the question is that quantitatively, how fast this happens, okay? And the reason that I relate my Langevin dynamics to underdamped Langevin dynamics is because for the overdamped Langevin dynamics, the Fokker-Planck equation just looks like this. Okay, so this is diffusion part, this is drift part. And the convergence of the Fokker-Planck equation is very well understood because this operator, the generator of this equation is self-adjoint, and it's also cohesive with respect to the measure. In other words, you expect a Poincare inequality. Okay, so this is Poincare inequality for the measure that we're interested in the x variable. Okay, by the way, I should emphasize that in the overdamped equation there was no velocity variable, right? So that all these things are in x. Okay, while here in the underdamped there was of course a velocity variable. Okay, so this Poincare inequality for the measure in the x. Okay, so that this is like the h minus average square is bounded by the gradient of h square, right? So it's the usual Poincare. And now, if you have a coefficient here, like 1 over m, where m is a constant, okay, and using energy method, and you just plug in the L2 norm into the equation and then differentiate it using the equation, you very quickly realize that actually this L2 norm will exponentially converge, and with a convergence rate actually given by this m, the Poincare constant, okay? And you may ask, okay, when the Poincare constant is known, for example, if U is a strongly convex potential, like a quadratic potential, and M being its smallest eigenvalue of the Hessian of the potential, in other words, the U is M strongly convex, then we know that this M is exactly this M, the convexity parameters of U, and we know that this converges with a linear rate that is M. Okay. So one question that we would like to ask is that, is there any improvement by the underdamped Langevin dynamics? From a physical point of view, this is reasonable to ask because as we see that when we derive the overdamped Langevin dynamics, we need to send friction to infinity. This would mean that actually the dynamics become slow, right? Because the friction is very large, so things move slowly. So now the question would be that for the original Langevin dynamics, what is faster? And also from a mathematical point of view, this is also a very natural question because if you, I think actually this afternoon, Michael Jordan will talk about these things. And if you think about the recent, if you look at recent literature of optimization, one thing is that, if you replace the steep descent, which in the continuous language, which is the gradient descent flow, if you add in a momentum, you get so-called accelerated gradient descent. Okay, and then, for strongly convex potential, we know that for the accelerated gradient descent, the convergence rate is exponential, and with the convergence rate, it is square root of m. Okay. Now, if we if we take away all the noise from our dynamics, then we realize that actually the Langevin dynamics is essentially accelerated gradient descent. Okay, and similar as overdamped dynamics is just a noise-perturbed version of the gradient descent, right? If we take analogy between optimization, so the first line here is algorithms for optimization. The second line here is algorithm for sampling, right? If you think about, okay, so this is an analogy between optimization and sampling world. Since in optimization it's well understood that this is convergence rate with M, this is convergence rate with square root of M, we would hope that if we run the underdamped Langevin dynamics, the convergence will be accelerated from M also to root M. Okay? So this is kind of the expectation. Even though, I mean, this result, I think with our work is open in the literature. Okay, so here is our result, the main result of the first part. So what we can prove is that if you have a U that is convex and satisfies some regularity condition, this just essentially means that U is not too crazy, growing too fast. Notice that even if U grows exponentially fast, this can be satisfied. And also, you want U to not grow too slowly, because otherwise, convex potential can be flat, and that the invariant measure does not really exist in the whole space. So we also require that U grow superlinearly. Okay, this is from PDE point of view. This is to make sure some compactness in the sublift spaces. Okay, then we can establish this convergence rate result for the underdamped Langevin dynamics or the kinetic Fokker-Planck equation. Okay, so that on the left-hand side, this is just L2 norm. Remember that this integral is constant in time, so, and then I always need to subtract off because the f will converge eventually to the constant. And the right-hand side is the L2 norm initially, and then with a constant C not here. The constant does not depend on M, and then there was exponential convergence e to the minus lambda t. The important part of the result is that we can get a fairly explicit estimate of the lambda. In particular, as a stated result here in the convex case, there are some more, we have some results for the more general case, and you can read our paper for that. And for the convex, so this is expression for lambda, where C0 is also a universal absolute constant. Okay. In particular, if you choose the damping parameter, the friction parameter gamma, to be proportional to root M, then you see that this convergence rate becomes also root M. Okay. Which is what we want to prove, right? Okay, so let me discuss a little bit this result. So this is essentially the thing we established. Now for simplicity, I set the constant to be 0. Okay, first of all, I should say that this order root M result is optimal. There is no way to improve beyond this, because we can do explicit calculations when U is simply a Gaussian, even in one dimension, and you can explicitly calculate that the convergence rate is root M. Okay. Proportion to root M. So this is the fastest thing that you can get. And also, as I mentioned, that this, as far as we know, this is the first result in the literature with the sharp root M convergence rate. There are, of course, many previous results on the convergence of underdamped Langevin, which I will also briefly review later. But as far as we know, this is first result with explicit constant and with a root M dependence. Okay, and also, we state this result from a PDE point of view, so that we say that L2 convergence of the backwards Fokker-Planck equation. But actually, in L2 convergence of the kinetic Fokker-Planck implies the convergence of the forward equation, the density, in chi-square divergence, and also because chi-square is stronger than relative entropy and total variation, so that if you want the result in terms of this metric, the convergence is also in root M. We do not know Wasserstein, which is actually an interesting open question. So that, for people who are interested in optimal transport, that would be a nice question to consider. So what's the convergence rate in Wasserstein distance? Okay. And also that point out that, if you compare with the result, convergence result with overdamped, the C0 there is 1 in the overdamped case, because it's just energy method. It's very simple, ground wire inequality. But here, this constant is generically larger than 1, and it's not avoidable, okay? Because if you don't have C0 here, then this result is certainly wrong, okay? Because this was implied that my operator, the generator, is cohesive, which is not true, okay? Because, this is well understood. Because, if you go back to a kinetic Fokker-Planck equation, you realize that if you look at the generator, it has second derivative in V direction. But in the X direction, it only has one first derivative, right? So that this operator is actually not elliptic. So in other words, and also it's known that it's not coercive. And the operator is so-called hypoelliptic operator, which concept dates back to Lars Homander, in the fundamental works. Because, as I said, diffusion is degenerate in X. It is some kind of weakly elliptic because you can hope that this vector field in the rotational vector field due to Hamiltonian will help you to kind of transport some of the diffusion in the V direction to the X direction, right? But this is subtle, okay? So that you cannot simply using a coercive estimate. And in particular, this is what I just said, right? In particular, we cannot hope that the exponential convergence will follow from the coercive estimate of the generator. Okay, you need to establish so-called hypocoercivity. And this has been a widely studied topic in recent years in the PDE literature. Of course, the kinetic Fokker-Planck equation, the analysis is by Kolmogorov, but related to our analysis, the results on convergence, so there are many results on convergence. For example, in 2009, Villani has studied convergence in the H1 norm, which is actually where he established the notion of hypocoercivity. Okay, and now this result, the constant is fairly implicit so that you cannot actually track what the convergence rate is. But then in the effort trying to make the convergence rate more explicit, so this very well-known paper by both Mahou and Schmeiser in 2009, and also a later paper, and they established a modified L2 norm and tried to get a convergence in modified L2 norm with a better constant dependence, more explicit constant dependence. And in particular, this was applied to the kinetic Fokker-Planck equation by Roussel and Gabriel Stotz 2 years ago. But if you check the constant dependence, actually the dependence on M is not sharp, so that you do not get the acceleration. And I mentioned before that already that we do not have convergence in Wasserstein in our work, but there are also a lot of interest in studying the convergence in Wasserstein, even though the rate is not optimal. I think the best rate that you get is M. Okay, so from these works, for example, by Dalayan and his student. All right. So now I will talk about a little bit of the analysis. I don't think I have a lot of time. So as we said, that this problem is hypocoercive. So the point is to establish coercivity. And then our analysis is actually quite strongly inspired by a recent work by Scott Armstrong and Jean-Christophe Murat in 2019. They studied kinetic Fokker-Planck equation on compact domain without potential. So it's just a flat thing. And they established a variational framework, which kind of putting very nicely the bracket condition that dating back to Homander into a variational framework. Okay. And essentially, our idea is to kind of get inspired from this work and try to modify their variational framework to take into account of the dependence in the X position in the potential. Okay, so there are some technicalities that we need to overcome, but I think the initial idea really comes from this variational framework. Okay, so one of the main ideas is that because this L is not coercive, we have to utilize the fact that as you propagate in time, the diffusion in the V will be transported to the diffusion in the X. Okay, so we still want to establish a Poincare inequality. But as we said before, that it's impossible to establish Poincare inequality just in terms of X and V. Okay, but now if you lag the time a little bit, right, so that we actually now augmented the state space by putting a time interval on top of X and V, and equip it just with a Lebesgue measure, and we think of this equation as a whole. So we consider the operator derivative mean time minus the generator, and the idea is actually to establish a Poincare inequality for that. Okay, so that we can use the fact that in time this thing will becomes coercive. Okay, so this is the kind of the result. So now let me just some notation. The kappa, let's denote the distribution in velocity, which is just recall that it's just a Gaussian in this case. By the way, I should mention that this analysis technique can be generated to other kinetic type of equations, which was also part of the original motivation by the work by Armstrong and Murat. And we can do, for example, linearized kinetic equation as well, but I'm not going to talk about these things here. Okay, so now we can establish this Poincare inequality. So the first line is like what you kind of expect from the usual Poincare, right? This is the derivative in V. Okay, but as we said, this is not possible, especially if you look at this Poincare inequality. If you send t to 0, then you see that this constant blows up. So that if your time interval there was no time interval, no time lag, then it's impossible to establish Poincare. And then the fact is that we need this help of the antisymmetric part of our equation. The delta t minus the generator, the Hamiltonian part, and this derivative to help. And then because this derivative is a bit too large, so that we consider it in the negative subgroup space. Okay, the order, to match the order. All right, and then these constants in the end of the day comes to the constant dependence that in our final estimate of exponential convergence, and by choosing, for example, t, the lag time is 1 over the square root of n, which is like the time that you should expect some half decay of the divergence. Okay. So due to time, I don't have time to go into details of the proof, and which is the key part is actually solving a divergence equation, and which actually is kind of technical. But if you're interested, we can talk offline, or you can also, of course, read our paper and ask me in email if you have any questions. Okay. So now the second part talk, I'll talk about generative models. And now, I'm not going to give you a very large overview of generative models and how it's used in machine learning, but for my interest, for the talk purpose, we're essentially interested in using generative models to sample distributions. And now how this works, right? So the basic idea of generative model is the following. Suppose we have a very simple distribution to start with, and usually people start with Gaussian. Okay, so let's denote it by P of Z. The idea of generative model is build up a function, which we call G, and to push forward this distribution to something. And we hope that after push forward, this distribution actually approximates a distribution that we desire. Okay, we want to sample, for example, say that pi is a very complex distribution, and then hopefully we can find a function G such that we can push forward this. In this talk, I'm not going to talk really about GAN. Like for example, my pi, I will assume always that my pi is given, okay? And I'm not, in the usual generative model setting, in the machine learning case, the pi is given by empirical measure, some sample points. But here, I would really want to turn the question around to ask that, suppose my pi is specified, PZ is also specified. And I think the first question that people want to ask is that whether there exists this function G such that you can push forward this, can source distribution such that it gives a good approximation for a target, right? And if you're familiar with the machine learning literature or the neural network literature, this is kind of like asking, there were these results, for example, by Andrew Barron, saying that if you give me a function, I can build up a neural network to approximate your function, right, with some rates that depends on very mildly on dimension. These results are called universal approximation results. And here, the question we want to ask is actually just an analog of this kind of question of universal approximation on the level of distributions. So we want to say that if you give me a distribution, whether you can find this map. And I think before our work, this question is rarely asked. And I think the only thing that in literature we found is this work by Holden Lee, who is actually also now a postdoc at Duke, and Rong Ge, a colleague at Duke, and together with other collaborators, including Tenyu Ma, Andrei Ristevsky, and Sanjeev Arora. They ask a question. Their question is slightly different. They're saying that essentially, if you know that the distribution is given by a push-forward map, and the push-forward is a Barron function, then whether you can find it, how much you can approximate that, right? But we want to ask a more general question, saying that I just give a distribution to you, which is pi, and whether you can find a push-forward. Okay, so of course, to ask this question more quantitatively, I need to make more. I need to make it more carefully. What this approximation means, right? Need to become more quantitative. And now, the specific metric that we are going to consider in this work, to measure the difference between two distributions is known in the stat literature as the integral probability metric. I think this is also quite popular these days, in machine learning, which is the following, right? So that you want to ask how much different is P with pi, two distributions, okay? You want to find a divergence, a metric between them. And the thing that you do is that you kind of look into weakly, this kind of like looking at a weak convergence, right? You test it against a family of function. Then you take the soup over this family of function and look at the difference between the expectation of the function under the first distribution and distribution of the function on the second distribution, right? And related to the GAN literature, if you're coming more from machine learning, this F is kind of like a discriminator, okay? All right. And in particular, we are going to think about consider three kinds of IPM, the integral probability metric here. The first one is perhaps people like, especially in this program, like this is the one Wasserstein distance, where you just take this class of function to be the one Lipschitz functions. And I write another form to represent the Wasserstein distance in terms of the coupling between the two probability distributions. Right? This is a collection of joint probability distribution that the first marginal is equal to p and the second marginal is equal to pi. And this is one Wasserstein because I use the L1 distance here, right? One Euclidean distance here. Okay. And another popular metric that's being utilized, especially in this machine learning literature, is the so-called MMD, the maximum mean discrepancy, where this function fd is taken as a unit ball of the reproducing kernel Hilbert space. Okay, and if you do not know what the reproducing kernel Hilbert space is, you don't need to worry, and because I'm not going to the details anyway. But this is kind of like a weak Sobolev norm, from a PDE point, negative Sobolev norm from a PDE point of view. Okay, and now the other metric that I'm going to consider, I think on Tuesday there will be a talk on Stein discrepancy. So that people have also been considered in the machine learning literature on the kernelized Stein discrepancy, where, so that you measure, this is fundamental work dated back to Stein, you can measure the difference between two probability distribution using the Stein operator, which is the operator is defined like this. And as you can see that if you take the adjoint of this acting on, if p is equal to pi, then it will vanish, right? Because because simply this is log of pi and this is gradient, and you can act in these things on pi. So that this would give you 0 if p is equal to pi. And then, this is not a metric, this is asymmetric, but it can be used to measure the distance between, the discrepancy between two probability distributions. Okay, so in general, what you take is that you take a function f, and again, we assume that test function class is in a kernelized space. Okay, so this is why it's called kernelized Stein discrepancy. And you take the f, all possible f, you take the Stein operator acting on that, and then you take expectation of this with respect to p. Okay. Even though that I write in this way, but this is actually also a IPM, because as I said, if you take expectation of the result of the Stein operator acting on f, it's always going to be 0 if you take expectation with respect to pi. So you can also write this as e expectation of p minus expectation of pi of the same thing. Okay, except that my test function has been is the result of a Stein operator. Okay. Sorry, it's a very quick overview of how to measure distance between the probabilities. And now, specifying this, our main result is actually the following. So we consider the source distribution to be absolutely continuous with respect to Lebesgue. Okay, so for example, PZ is a Gaussian. Okay, and now the claim is that there exists a fully connected and feed-forward deep neural network, U, okay, such with depths given by log of n, and then the n is a complexity parameter that we specify the neural network. So this is depth, and the width is essentially n. Okay, such that under this the discussed discrepancy, the push forward of my source distribution by gradient of u. Okay, u is my neural network, and then I use its gradient to push forward the source distribution. And if I compare that with the target distribution, I want to ensure that my accuracy is below epsilon. The question, so this part of it is not really the statement. This is really like what we want to do, right? The actual statement is actually how the complexity scales with epsilon, okay? And it actually depends on how you choose the metric, right? So if you choose Wasserstein, okay, and as we know, Wasserstein is a very stringent measure in terms of probability distributions in higher dimension. Okay, so there are, for example, if you think about how fast the empirical measure converges to the measure in the Wasserstein distance, you know that we have curse of dimensionality. And it's also not surprising that in our context of the generative model, we also facing curse of dimensionality. For some technical reasons, we need to assume pi has finite third moment, but this is just a technical assumption. And then what you get is that this is the rate. Essentially, this is, yes, n is actually epsilon to the minus d, right? So that this is actually super large when epsilon is small and when d is large, okay? And in lower dimension, this Wasserstein 1 is okay, but if you go to high dimension, and this becomes too stringent to measure, and so that we need a really complex neural network to push forward things. Now, how about the other? And actually, the reason that people introduce MMD and also KSD in the stat literature and in machine learning literature is the hope that they can overcome the curse of dimensionality. Because MMD is essentially a negative norm, right? So that in high dimension, this behaves better. And in fact, we can prove the following. So that if you choose MMD metric to measure the probability distribution, then the complexity of the neural network is just proportional to 1 over epsilon squared. Okay, and all this implicit constant here is independent of anything, independent of dimension in particular. Okay, so there is no dimension dependence here, which is very nice. And also, if you want to measure things in KSD, and people are also trying to do generative models using kernelized standard discrepancy these days, and plus some technical assumptions, which I'm not going to talk very much, but some regularity assumptions for the probability distribution, and also we need to assume some concentration. Okay, so that is sub-Gaussian. And then you get the result that n is actually equal to d over epsilon. Okay? The epsilon is slightly better than the epsilon here, is because after applying the Stein operator on the test function, there was some cancellation, so that it actually gets one weight higher. Okay? And for people that are familiar with GAN, one question that may come up is that here I'm using the gradient of the neural network to push forward things instead of the neural network itself. Okay? And the reason for doing that is simply because U has better regularity. So you can think of the following very easy example, right? Suppose that our PZ is just a uniform distribution on the interval from 0 to 1, while our target distribution is 2 Dirac points. Okay, one concentrated on 0 and another concentrated on 1. And you can easily see that there is no continuous map that you can push forward the uniform distribution, the back distribution to this Dirac mass, the sum of Dirac mass, right? Because you have to split at some point and say that, okay, so this part goes to left and this part goes to right. So the push forward map itself is actually discontinuous. But if you parameterize it using the gradient of U, then the U can be it's a Lipschitz map. Okay? Okay, just you can. I didn't put in the plot of that, but you can. You can see that actually U is just essentially an inverse hat function. You push forward things to left and push forward things to right. Okay, so that actually the U is better object to parameterize. Especially if you consider kind of problems where pi is maybe discrete. Okay, so that we consider U because U has better regularity. All right. So with the remaining time, let me tell you a little bit how this proof goes and why I talk about this in this workshop, because I think there is related to a lot of interest in here. The technique is actually very similar to the standard approximation theory. So the idea is that for all these probability distributions, we want to take first a sieve to approximate any arbitrary distributions, and then we're going to construct explicit approximations for the elements in the sieve. And the sieve that we consider is actually this summation of Dirac masses. Okay, so the first step of the proof is to essentially to approximate pi by empirical measure, and which the xi is IID samples from this measure pi, and we consider empirical measure that is pi n, which is just 1 over n of these Dirac mass, sum of Dirac mass. And now the approximation rate between the pi n and pi n, this has been well studied, for example, for Wasserstein distance. There are maybe some earlier works even, but we are citing these more explicit works that with a more explicit characterization of the convergence rate. Okay, and in particular, one of the recent work by Jing Lei, who is a colleague of Zhejiang at CMU, who give a very nice clean result of the convergence rate of Wasserstein of the empirical measure. And now in MMD, this also has been studied before by Sperber Boulder. Sorry, I cannot pronounce this name very well, in 2016. And for KSD, as far as we know that our work is the first result with a very explicit convergence rate. Okay, and now after this step, right, so we just need to push forward something to the empirical measure because, using triangulated inequality, right, so that the pi is well approximated by pi n. So now we just need to approximate pi n under the push forward. And this step can be done using the theory of semi-discrete optimal transport, okay? Because what our goal now is to push forward a measure that is PZ, and which we assume that is absolutely continuous with respect to the back, so it's a continuous measure, and we want to push forward to it to a discrete measure, which is given by the sum of the empirical measures. Okay, and now, I guess there are many experts, but just for the general audience, this is very quick overview of the optimal transport, and I'll tell you why we can do this for the semi-discrete case. Okay, so this is the Munch formulation of optimal transport with quadratic laws. For this part of the proof, we are going to use quadratic laws, okay, because we are going to use Brownian formulation. So, and then as well known that, Kontorovich realized that this is too restrictive. Essentially, it cannot, essentially because T cannot split mass. So that Kontorovich formalized a convex realization of the problem, which is this. So that now you look at the coupling of the measures and you want to minimize this Euclidean square norm. And of course, Kontorovich is essentially the first one who introduced linear programming. And this is a linear programming problem. And Kontorovich realized that you can look at the dual formulation of the linear programming. And this is the Kontorovich dual. Okay, so instead of looking at the coupling, you're looking at two potentials, okay, phi and psi, such that they satisfy this constraint, the cost becomes constraint, and this the constraint becomes cost, okay? And also because of, the nice structure of the problem, you can also just explicitly write down what should be the optimal of phi using the C transform. Okay, you want to take all the infimum of the of psi that satisfy this equation. Sorry, okay, so I'm a bit rushing myself. So that this is a C transform of the psi function, and this actually gives you the optimal phi. Okay, and this problem is nice because now you just have one single function to optimize. All right, and now our case, okay, so yeah, I should mention that, so we are going to use a fundamental result by Brownian, and that assuming that the mu is absolutely continuous with respect to the back, okay, then there exists, there is a connection between this this potential here, which is given by the C transform, with the optimal transport map. Okay, so the optimal transport map is just given by the gradient of phi bar, which phi bar is intermittently related with the phi, which is a Kontorovich potential. Okay, so the phi bar is known as Brownian potential. All right, so now for the remaining minute, let me tell you, what's the semi-discrete optimal transport of what we use here. So recall that our goal is to transport a source measure, okay, which is absolutely continuous with respect to the back, so that we have a density rho, into a bunch of delta mass, okay, which is our target measure, which is semi-discrete. So you can write down in the discrete case what's the Kontorovich dual, right? The Kontorovich dual becomes easy because one of them is expectation of psi C transform, and another of them is psi expectation with the target. And now in this case, the target distribution is just a Dirac mass, right? So that expectation with respect to target is just given by the finite sum here. And because of this, right? And remember that psi C is given by the C transform of the, so this is C transform of psi. But because psi is a kind of a discrete thing, so the C transform we can also written down very explicitly. So it's just this function. Okay. So compare with before, right? In the continuous case, where in principle you need to find the psi, which is infinite degree freedom, which is L1 function. Now we just need to find n points, right? N numbers, psi j. And after you find psi j, then this thing is completely determined. So actually the Kontorovich dual becomes an optimization problem in Rn. Okay, you just have n variables to optimize. And what's even nicer is that, this is the result is first known in the compact domain by a work by David Gu and with others and S.T. Yao in 2016. And we extended to the case result on Rn. Okay, so in particular, in this case, you can check that there is also a discrete analog of the Brownian theorem, saying that optimal transport plan is essentially very easy. It's just a gradient of a potential phi bar, the Brownian potential, which is a maximum of some linear functions. Okay, and this is a piecewise linear function, and so you have n piece, and in each piece, essentially, you just kind of merge together all the mass in there into the Dirac mass, into Dirac delta. Okay, and also because of this is just a piecewise linear function, right? So you can easily approximate a piecewise linear function by ReLU. Okay, ReLU is a piecewise linear function, and you can easily construct a neural network to approximate it, to actually parameterize this. So this is actually the idea of the proof. So first, we approximate the target distribution by its empirical distribution, and then we use semi-discrete transport to show that you can just transport the source measure, which is Gaussian, for example, to the Dirac mass. Okay, so I think my time is up. And now, I mean, essentially, just to summarize, we talk about two things. I mean, just using PDE tools to understand the convergence of underdamped long-Japan dynamics, and also using optimal transport theory to understand the universal approximation for generative models. One thing I should emphasize is that if you are satisfied with using MMD, which is actually what people are trying to do in machine learning these days, or using KSD, then indeed we have universal approximation results without curse of dimensionality, okay, for generative models. All right, and this is all of my talk. And if you're interested, the references are on the archive, so that the first one is this number, archive number. And the second, we submitted the work, and now I think it should appear on archive today, if there was no delay. All right, and with that, I want to conclude my talk, and thank you for your attention.